Hello and welcome back to another math video. This time it's Pi Day 2023, so I guess I'll do, actually this is not really that pi related at all, but actually it is a little bit. So we're going to be doing Taylor series. I'll be explaining the fundamental idea behind how they're made and why they're used, and then we're going to do a short example with sine of x, or probably e of x, to just make a Taylor series for that function. Alright, so first of all, Taylor series, why do they exist at all? So I'm kind of tired of writing out everything. Okay, I guess I have to write it. Taylor series, not to be confused with Taylor Swift, are a way of approximating a function. Let's say you had like f of x equals e to the x, and then this function kind of looks like this, and you wanted to approximate it using a polynomial, which is kind of faster to calculate. And let's say you wanted the value at, I don't know, x equals 1, maybe it's up there, and you know the value at x equals 0 because it's simply 1. And then you want to get to whatever value it is at x equals 1. Now, sometimes, you could just plug it in. That's one way to get the value. But other times, it's actually kind of harder to do that. Like if you had a really complicated function that it took longer to compute, you might want to do that, millions of times or billions of times. So perhaps you would actually rely on a polynomial calculation, which is a little bit faster, and you'll get a slightly off approximation, but it might work for your purposes. It's all about the trade-off between, the speed and the accuracy. But anyway, the idea is you want to approximate a value of a function that's a little bit away from the value you know, or the value you're starting at, and then it should be faster. So basically make a polynomial, it approximates a function, and then you can do calculations with it. Now the problem is, how do you make this polynomial? Well, basically at the value you start at, you have to match all of the nth order derivatives. So let's say you had like the first derivative, the second derivative, you can calculate all of that beforehand for f of x. In this case, for e of x, we have, of course, e of x all the way down for every single derivative. So, like the first derivative is e of x, e to the x, and then so on, down to however much precision you need. In most cases, maybe like, I don't actually know how many terms people use, but obviously the less you use, the faster you can calculate because the polynomial is shorter. But also the longer the polynomial, the more accurate. Now, the series is basically just, like a sum. And then as you go on to higher order derivatives, you'll be able to get closer to the true value. And assuming that you have an infinite series, you will get the true value. But let's just do like a couple terms here and there to demonstrate the idea. So we have the basic value, first derivative, second, third, and then I guess like we could do the fourth as well to demonstrate the idea. Alright, so this is our rows, and then we're going to need e of x, and we actually do need the value at 0. So the basic function is e of x. First derivative is going to be e of x. I'm just going to write e of x for all of these. So that's good. Now we calculate the value at 0, and it's all 1. Very interesting. Okay, so now we know the function we want has these derivative values at x equals 0. Note that this is just at x equals 0. This is not true for anything other than at x equals 0. Alright, so now that we have this, we can try to make a polynomial. So let me get rid of this. We can move our table down here. Alright, looks good. Okay, so our polynomial, we're going to start at the lowest order term, which is x to the 0. Now every polynomial you can write it as, let's call it g. So g of x is going to equal, some constant, let's call it c0 times x0 plus c1 times x1, x to the first power, and then, so on, until you get to like whatever you want, c sub n, x to the nth power, and then it goes on to infinity. So the idea here is the x to the 0 term will match to f of 0. This is f prime of 0, by the way. Alright, so that was interesting. Alright, and then the x to the first power will match here, because when you take the derivative of g of x, you're going to get kind of this term will become removed, and you'll be left with all the terms from afterward. Alright, so let's begin at x equals 0. What's the constant going to be? So here, f of 0 equals 1, so we can just have 1, basically. So this is going to be the start. It equals 1. And then what's next? So the next term is right here. So we want the first derivative of x to the first times c1 evaluated at x equals 0 to be 1. And when you differentiate x, you get 1. So c1 can just be 1. So that means c1 is 1. We're just going to add x. What's next? Well, we get x squared, right? And then when you differentiate x squared, it becomes 2x. Well, we're going to take two derivatives. And you do it again, it becomes 2. So 2, that's not what we want. So we're always going to do like 1 over whatever number we end up with will become the constant. So in this case, 1 over 2 times x squared. Now for the third term, or the third order of x, the third order derivative of x. So here, x cubed, that turns into x squared, turns into x, 3x squared, turns into 6x, goes into 6. So you might be able to see a pattern here. So, okay, let's just first put in our number here, or our the fourth term of this series. So you can see the pattern probably. So when we go from here to there, the first time we differentiate, we use, the power rule. We take that number down from the top, from the exponent, and then we move it in front. We multiply. So we times 3 there. So this is the kind of scalar in front. And when we go here, we times 2. And when we go here, we times 1. So the pattern is kind of just multiply all the way from whatever number you have in the exponent down to 1. So like times 3, times 2, times 1. And then the next pattern, you can probably guess it. What's it going to be? Well, x to the 4th, we go to 4x to the 3rd, goes to 3 times 4, x to the 2nd, and then we go to 2 times 3 times 4, x to the 1st, and then it becomes 1 times 2 times 3 times 4, oops, is our answer. I'm not gonna deal with this. Alright, so that's what we get, and then obviously we have to do 1 over that number for our C4 in front. So the pattern is just make C 1 over that particular product. And that product, when you multiply everything from n down to 1, and so on, times 2 times 1, this is known as n factorial. So that's the mathematical term for when you multiply every integer down from the current one you're at, down to 1. So that's n factorial. So instead of writing, like 6, you could have written 3 factorial. So they're both right, but if you're doing like computations, it's better to think of it as 6. If you're doing it like theoretically, like right now deriving it, you're going to have to use the factorial to calculate what value that is. But at like the running time for your maybe like approximation that you want to do like a bunch of times, like a billion times, then when you use this series, you're going to have to use obviously not factorial, because that would take longer. You would have to do the calculation again. You're going to use the regular number, 6. So here, 4 times 3 times 2, that's 12, times 2 is 24. 1 over 24, x to the 4th power. And then we can continue on. So what's the pattern here? What is the nth term? Well, we have 1 over n factorial as our constant, and then x to the power of what? X to the power of n. And n starts at 0. Now you may be wondering, well, what if like n is 0? Did I actually say that already? Okay, so if n is 0, what happens to this term? There's no problem here. That's just going to be 1. But what is 1 over 0 factorial? Well, first of all, what is 0 factorial? 0 factorial we can derive using this pattern. If we go backwards, so 3 factorial equals 4 factorial divided by 4. You can kind of figure that out for yourself. This is true. And then 2 factorial equals 3 factorial divided by 3. And then 1 factorial is naturally 2 factorial divided by 2. So what does that mean? If we continue the trend, which is kind of what mathematicians do. By the way, I didn't come up with this idea. I learned it from like this professor, I think. I don't know who it was exactly. Might have been Po Shen Lo. Probably him, yeah. Okay, so the pattern here, if we continue, 1 factorial divided by 1. And what is that? It's 1. 0 factorial equals 1. Alright, so anyway, back to the main point there. The nth term equals, and we're starting at the 0 index, by the way. We're starting at 0. So the nth term equals x to the n over n factorial. And then obviously, you can have infinitely many terms. So if we were to write the whole series, the infinite series, which is kind of what the Taylor series is, the Taylor series is not like it stops at n. It goes on infinitely. So if you're on like the AP test, you would have to write this. you have to write plus n factorial. Oh no, it's actually n over n factorial plus that stuff. These are ellipses. It's kind of like assume that there's stuff in between that follows the pattern. And when you add it at the end, it means it goes on infinitely. So the whole thing would be g of x equals this. Now, on the contrary, if they say like just write the first, like 3 terms, then you don't need this. You don't need the stuff afterward. Actually, it might actually hurt you to write more than the first 3 terms, assuming that's what they wanted. All right. So what are the key takeaways here? Well, Taylor series are a way to approximate values at. Actually, we should maybe run a value check. So let's see what is e to the first. So basically, what is f of 1? So from here, we're going to write approximates g of 1. And let's just take like the first 3 terms. So kind of looks like we have 1 plus 1 plus a half. Okay, so that gives us 1 plus 1 plus 1 over 2 equals 2.5. So is that correct? Well, e to the first power equals like about, let me write approximates again, 2.71, I believe, or 2. Okay, so 2.71 is the value here, 2.718, I believe. So that's the true value. Our value is 2.5. That's only off by like a little bit. If we add the next term, we'll get well, 1 over 6 is I think it's like, what is that? 1.666. I think. Wait, no, I mean like 0.166. Let me do that in my head. Yeah, it is that. So if we add this on, it'll become 2.666. All right. So that repeats. You can see how it gets closer and closer and closer, and that's the power of having Taylor series. And so anyway, key takeaways from today: Taylor series are a way to calculate things faster in the computer. Maybe not like in real life. Like you might not like do it by hand. I don't mean in real life, I mean by hand. So it's not only faster by hand, but in the computer, if you were to want to approximate a value like e to the first power, you might make a Taylor series to do that. You could also approximate square roots to some approximation. So basically, you can use the power of matching the derivatives at a point in order to move it forward along in x so that it'll be close to the future value, or the adjacent values of that particular point. So I think the most important thing here to understand is how we came up with the constants to put in front of the x terms. So like C0, C1, C2, how do we come up with that? And it all comes down to when we take many derivatives, we'll have these leftover terms from doing the power rule a bunch of times. And when we do 1 over those values, we end up with the pattern of n times n minus 1 all the way down, known as a factorial. So I think that's the most important lesson to take away, is how do we come up with things without knowing in advance what they are. Of course, I didn't know in advance about this concept, but my hope is that you guys will understand it more intuitively than I did when I started learning it through these examples. And don't worry, it takes time to understand things properly. And I had to do this video like 3 times because I couldn't explain some things very well. Probably in the future, I'll look back on this video, I'll still be like, there's some problems with this video. But that's all a part of growing up and becoming a math teacher. I'm just kidding. Alright, so that's it for Pi Day 2023. Thank you guys for watching, and see you guys next time.